Альберт Николаевич, звук выключен у вас. Звук выключен.
А так слышно?
Отлично.
Yeah, отлично.
Dear friends, today we begin our seminar. Seminar of Department of Probability. And the first speaker is Luigi Accardi from Roma. I know him, I know his talk probably more than 40 years ago in Moscow University when Luigi was very young. And still now he has very good contact with the people from Moscow University and from Stokholm Mathematical Institute. I remember very well the following situation. Many years ago, I asked Luigi organize special memorial day for Kolmogorov in Roma during the conference on stochastic processes. Program was completely forced, and it was no time, but Luigi was very brave that he funded not only one extra day for this memorial meeting, but also he funded money for invitation of the 10 people from the Soviet Union. And as a result, we had a very good meeting headed from our side by academician Nikolsky. And besides of all, I want to say that we know Luigi by his book published in Springer in 1902, it seems me, under name Quantum Theory and its stochastic limit. Yes, Luigi, correct?
Yes, correct.
Yes, and he also had several papers with Arefьева, Volovich, Pechin from our institute, and several his papers at least by name are very familiar to us. For example, paper about a white noise approach to the stochastic calculus, quantum stochastic equation for the low density limit, and so on. So I think that the talks of Luigi today and next week will be very useful for probabilists, because in fact we understand that there is a big group of the people, for example, Luigi, Volovich, who are doing the quantum theory of probability, but from another side, we have big groups, in several groups who are doing stochastic calculus, and so it's necessary to understand what they are doing, what we are doing, and so Luigi, it's very nice. By the way, I remember but several papers of the Luigi had name Fermi. And so it was it's very pleasant that in fact we have representatives of this school in our seminar. Luigi, please.
Thank you very much.
Dear colleagues, please, we have a tradition. You can interrupt the lecture by your questions, but now, as usually, everybody please turn off their video and their microphone and connect a microphone only you have some question. Please, Luigi, you have 1 hour.
1 hour from now. Very
From
good,
now.
because I can share the screen. Okay, can you see?
Yes, it's very good.
Can you see the screen? Okay.
Yes, yes.
So I am extremely happy and honored to give a talk to this seminar. It also reminds me, as Albert remembered, the times where I was much younger. Quantum probability was just beginning, and I was preparing my candidatka dissertatia in Moscow, and I gave several talks in the cafedra of probability theory. So for me, it's a coming back. So let me just begin, because time is short, and I hope I will be able to say all what I want to say. So this is the abstract that I have already sent you, but I want to begin with a few caveats to you, to say that what I am dealing with today is I had to select many topics, and so I have chosen to neglect important arguments like the various notion of stochastic independence and the associated central limit theorem, the general theory of conditions, the law of large numbers, large deviation, complementary pairs, Kolmogorov entropy, and all applications to physics. I will maybe in my second talk we will speak. Physics will be present, but not in the sense of application, like for example stochastic limit, where you really find physics results. However, what I hope is that what I selected is sufficient to give an idea of the huge possibilities of interactions between classical and quantum probability, not in a far future, but nowadays. So let me begin with some remarks. The first part of my talk will be devoted to some terminology, some notations, because sometimes there is a difficulty of communication between classical and quantum probabilities, just because the language is slightly different, but they speak exactly of the same things. So how, in general, you can make algebraic and therefore non-commutative any branch of mathematics. And there is a standard way to do this. Thus you simply replace sets by commutative algebras of functions defined on them, and then you replace commutative by non-commutative. So let us see how this works in the specific case of probability. You take a measurable space, and it is replaced by the algebra of measurable functions on it. This is a star algebra for the pointwise arithmetic operations, and the identity is the constant function equal to 1. A probability measure is replaced by a state on this algebra that is a positive linear functional, which is given by the probability, and which is normalized so that the expectation of the functional constant functional 1 is equal to 1. Remember, I will use the same symbol for a probability measure P and for the associated integral, which is a state on the commutative algebra on measurable functions. Of course, the domain of this state will be the family of all integrable, P integrable functions. Now, very often it's convenient to restrict to subalgebras because there is a very rich theory of algebras of bounded operators, like the von Neumann algebra or C-star algebras. And therefore, if we restrict the domain of functions, we can use the tools of these very developed theories, mathematical theories. So the typical example is to restrict to measurable functions, bounded measurable functions, or to integrable step functions, functions with a finite number of values. So for this reason, we have the following definition. A classical algebraic probability space is a pair AP, where A is an abelian Stahl algebra. You can think of L infinity, bounded measurable function on a measurable space, and P is a state, positive linear function normalized so that P of 1 is equal to 1. So we generalize this by dropping the requirement that the algebra is commutative, and we take an arbitrary star algebra and an arbitrary state. So when the algebra A is non-commutative, we speak of a quantum probability space. When the algebra A is commutative, we speak of a classical probability space. So we replace the standard pair of measurable space and probability measure by a star algebra of functions and a notion of expectation on this star algebra. From physics, this term state is come, and from operator algebra. But essentially, this is an expectation value. Okay, so as I said, the typical example is a bounded measurable function on the measurable space and the associated integral. So I always assume that the algebra A is an identity. Then we come to the notion of random variable. If we have a classical probability space and the state space, a measurable state space, and we have a random variable with values in S, which is the state space, the sample space is omega, and the state space is SB. So this random variable X uniquely define the star homomorphism, which to a bounded measurable function associate the composition of the function with the random variable. And so we have a bounded measurable function on the probability space. And you can prove the converse is true up to stochastic equivalence, because this isomorphism, using the fact, this isomorphism uniquely determines the probability distribution of X, because P, if you apply this to a characteristic function of a set, 0, 1, standard characteristic function of the set B, then the expectation of this function is equal to the probability of the inverse image of B, which is exactly the definition of probability. So the distribution is the composition of the state with this homomorphism. Okay, remember that I insist that I use the same symbol for probability measure and from the associated expectation value, which is called a state. Okay, so we give the general definition. An algebraic random variable is defined on the algebraic probability space and with values in B as a general star algebra, is an homomorphism, and now we don't require commutativity of these two algebras. And the distribution is defined as in the classical case, as the composition of the random variable J that is homomorphic with the expectation value of the state. Okay. Now, given the definition of random variable, we have a natural definition of stochastic processes, and with an arbitrary index set T, and a stochastic process with sample algebra A and state algebra B is simply a family of star homomorphism. So just like a single classical stochastic process is a family of classical random variable, a quantum stochastic, an algebraic stochastic process is a family of random variable, algebraic random variable, which means star homomorphism. Now we want to define when two processes are equivalent. There are many ways, but one way that we use is the correlation kernels, which are a particular case of the so-called joint expectation values. These correlation kernels, you see, are, you see, the number n is the same on the two sides of the equation, and then the expectation value depends on the choice of n indexes, and then you have the random variable JS. So this is a positive definite kernel. This is a positive definite kernel, and the following theorem gives us the analog of Kolmogorov consistency theorem for joint probabilities. The following theorem I don't formulate, I formulate it in a rather synthetic way. Any algebraic stochastic process is uniquely determined by the correlation kernels plus a set of compatibility conditions that I will not formulate because they are technical and they will not give you, would not give you more insight. Just the point is that there is a quantum analog of the Kolmogorov compatibility condition. And the theorem is that there is a one-to-one correspondence between algebraic stochastic processes and correlation kernel. The correlation kernel determines the process uniquely up to equivalence, and as it happens in the classical case. Okay, and here the fact that we take the state algebra constant is not necessary for the reconstruction theorem. We can take the state algebra depending on the index t, and this is used in stochastic geometry. For example, this is very, very frequent. Okay, now we pass to a special subclass of stochastic processes, which we call operator stochastic processes, and which are more similar to classical stochastic processes, because in classical probability, usually the notion of random variable as star homomorphism is not very much used. So this notion of operator stochastic process is much more similar to the classical notion. The idea is the following. For each t in the index set, we take a family of algebraic generators of the state algebra B, and you can think of this as the components of a classical random. We have the classical random variable t. It can be even a vector variable, classical random variable, and xti are the components. So we consider this then the operator random variable will be the image of the generators of the algebra B under the homomorphism T. So now we have fixed a family of operators and in the algebra A. So if we change the index set, because now we have the index T and the index of the component, let us say, so we have a larger index set, and we have a family of operators, of elements of the algebra A. So this is the motivation, and the precise definition is that an operator stochastic process is an algebraic probability space plus a family of elements of A. So do you recognize these elements will play the role of the classical random variables, only that in this case, in the algebraic context, the xt may not commute. Okay, so this is algebraic process is not what in classical probability is called the classical operator valued process, because a classical operator valued process presupposes a classical probability space, but here there is algebraic probability space. Okay, which can be non-commutative. Okay, so now I just want to remark that this definition is too restrictive. Why? Because if I take this product, if I take this random variable, they belong to A, but A is an algebra, and so all products belongs to A, and therefore P can be applied to them, and so it has P is a linear function which has complex values. So this modulus is less than plus infinity. And this in the analogy with classical process correspond to processes with mix and moment of any order. So the reason why we use the apparently abstract definition with homomorphism is that we want to include all stochastic processes, not only with stochastic processes with all moments. However, this simpler definition, simple class of stochastic processes, that is the pair of algebraic probability space and a family of its elements, is very, very widespread in algebra, also in quantum probability. From now on, we will consider only operator processes to make the language more intuitive. So xt are the random variable, they may not commute. Now we fix the index set to be the real line, and we associate to every process, so to every process, we associate the algebra generated by this process. This will be the analog of the sigma algebra generated by the random variable with index in the subset I of the Borel subsets of R. So in particular, we can introduce past filtration, the future filtration, and the present algebra. And if they are filtration, because obviously the standard relation is satisfied. So we have we begin to have a conditional, a framework of classical probability. Now recall there is a generalization of the notion of conditional expectation in the frame of C-star algebra and can be extended to star algebras. And we say that a Umegaki conditional expectation from A to the past algebra of T is a linear map with the following properties. It is a star algebra. It is a star map that is commutes with involution. And this is, you recognize here, the fundamental property of conditional expectation, because if I take expectation on AT, any element of AT behaves as a constant for the conditional expectation. This is the fundamental property also in the classical case. And of course, normalization. Okay, the crucial point is that not always in the quantum case, conditional expectation exists. If they exist, if such a conditional expectation exists, the algebra AT is called expected. So an expected algebra. And the family is called projective if whenever S is less than T, we have the standard notation, which is familiar in classical probability. Okay, this is, if I project first on the larger algebra and then on the small, I obtain the same result as projecting directly on the small algebra. So from now on, we will fix the probability space, the stochastic process xt, and the past filtration, and a projective family of conditional expectation. With this, we can begin to do something interesting. Namely, we can study the kinematics of operator quantum stochastic process. Remember, the index now, from now on, is the real line. Okay, then we can speak of the forward derivative, as in classical probability. The forward derivative is the conditionally expected value of the future increment. That is why it's called forward derivative, conditional with the conditional expectation xt et. So this is the forward derivative. Okay, I will not specify the limit because there is no time, but my goal is to try to give you the main ideas, not the technical details. So then we have the analog of the fundamental theorem of stochastic calculus. This name I found in a book of Nelson, but I don't know if maybe this was already known and used in classical probability. So the fundamental theorem of calculus says that a function is the integral of its derivative. But let us apply it to the stochastic derivative. So if the process X as a stochastic derivative, it is the integral of each stochastic derivative, but there is an additional term which has this property, and you recognize in this property the martingale condition, very familiar in classical probability. But more precisely, is a martingale with respect to the given family of conditional expectation. So this is a theorem. Now, every stochastic process that admits a forward derivative which is continuous has this decomposition as an initial condition, a integral of the derivative plus a martingale. Well, this is a difference martingale term. Okay. Now I will always use, see, in classical probability, martingale is the standard model for a noise, and so we will use noise and martingale as synonyms. Okay, and now let us apply this theorem to the structure of another familiar object in classical probability, which is multiplicative functions. If I have a two-parameter family, U, S, T, that satisfies this condition, you see, it's called a left multiplicative function. Left because the future increment is on the left, and the past increment is on the right. And then we have the following theorem, which is similar to known theorems in classical probability, which give the structure of a multiplicative function in terms of stochastic integral. So we take a strongly continuous left multiplicative functional with continuous forward derivative. Then there exists a two-parameter family of operators, MST, which have the following property. We use the following notation. If we have two processes, F and G, which are operator-valued function essentially, we say that the two processes are equivalent if the difference of their increment with t minus s equal dt is of order small o of dt. So the
dt is t minus s?
T minus s, yes, dt is t minus s.
Thank you.
Dt is t minus s. So this is the definition of equivalence of two processes. Now, we use also the notation that instead of writing U0t, we write simply ut. And the main result of the theorem is that ut automatically, under these assumptions, satisfies the stochastic differential equation with a drift, which is an operator drift, and martingale term, which is an operator martingale. You see, the martingale term is as this characteristic, which is the remnant of the multiplicativity property of U of the multiplicative function URS. And it is a difference martingale in the sense that the expectation on the past, S is less than T, remember, of the MST is equal to 0. Moreover, we have that the following limits, these limits correspond to the so-called oblique brackets in classical probability, namely the expectation of the square bracket. So this limit both exist, they are equal, and of course, you see, this is a product of an operator times its adjoint. So this is a positive operator. So this limit is always positive. This will be very important for the physical interpretation. So the drift of the stochastic equation is a canonical decomposition in two parts. One is the negative part of the oblique brackets of the martingale associated to the process, and another one is an Hermitian operator. You see, and the I is very important because we will see in a moment why. Now, moreover, always it comes from the theorem that the martingale part can be split into two parts. The part n is I times a self-adjoint. You remember that if I have a self-adjoint operator and I take and I consider this as the generator, suppose it doesn't depend on t. I suppose that I take the exponential, the one parameter group generated by this. This is a typical Schrödinger evolution. Okay, so we have the Martingale analog of the Schrödinger evolution, and the noise is divided in two parts. One is self-adjoint, and the other one is, you see, this is the square bracket in the sense of the Ito calculus, but is the compensated square bracket. So typically you understand that PT corresponds to, is the non-commutative generalization of a point process, and N will correspond to the diffusion part. So in fact, when P is 0, we will call that the stochastic differential equation that we have found, this stochastic differential equation here, is a diffusion of diffusion type. Okay, now the interesting point is that the converse statement is also true. That is, if we start with a forward derivative, namely a drift, and then which has the given structure, and with a martingale term, and we use also here the notation that the martingale, this is the difference martingale, but when we fix 0 as initial point, it's simply a martingale. Okay, and then we obtain this stochastic differential equation. You see, in this stochastic differential equation, sigma t, I have already emphasized that is positive. It corresponds physically to the dissipative term, and this corresponds to the Hamiltonian term, and this is martingale term. So now, you see, to have an idea, if you take the martingale term equal to 0 and the dissipative term equal to 0, this is just Schrödinger equation for a time-dependent Hamiltonian. Okay, so the quantum version of the algebraic formulation of classical probability leads automatically to a generalization of the Schrödinger equation, a stochastic generalization of the Schrödinger equation. Now, of course, I will not discuss this, but given a martingale, as we do in classical case, we can develop a theory of stochastic integration with respect to the given martingale. And so therefore, the stochastic differential equation in differential form, as I formulated before, has the usual meaning that it has in integral form in classical probability, where again you see the drift term and the martingale term. Okay. Now, in order to go further, we remember that in classical probability, stochastic differential equations are strictly related to Markov processes. So we want to discuss Markov processes to establish also in the quantum case the connections, also in the algebraic. I use algebraic because algebraic unifies classical and quantum. All what I said is true also for classical, is not specific on non-commutative. So the term algebraic is appropriate in this sense. Okay, now consider the process, the past filtration, the future filtration, and the localization. Okay, is associated to the process xt, as we explained before. Then when we have a stochastic, an algebraic probability space with a past filtration, we say that the past filtration is expected if there is an Omegaki conditional expectation onto the past filtration. But we also want, and this is fundamental, that this is compatible with the initial state. That is, the conditional expectation in classical terms, this would simply mean that ET is up to sets of measure 0 exactly the conditional expectation associated canonically by Radon-Nikodym theorem to the probability measure P. Okay, and in fact, this condition, this equation is equivalent to the well-known equation that defines the conditional probability in. Remember, P is the integral with the expectation value with respect to P. The symbol P is the expectation value with respect to P. Okay, so this is identically satisfied in classical probability. So in classical probability, the definition of expected filtration is trivial because every filtration is expected. However, this is not true in quantum, and we will see later on. Now we introduce a particular class of Markov processes that we will call expected Markov processes. Expected Markov processes, they are very important because they include, as we will see, all Markov processes that we can construct via stochastic calculus, classical or quantum. So I will explain in a moment why, wait a moment. Okay, so for this process, the transition from classical to quantum probability does not require new ideas, only new notation, only just replace the algebraic notation, the standard classical probabilistic notation, you replace with the algebraic notation. So we have the past filtration, sorry, here is a future filtration, there is a misprint here, and for each t we have a present algebra. Then we have a projective family of conditional expectation. Recall projectivity is the standard notion. And then the family ET is called Markovian, is the conditional expectation on the past of the future algebra is contained in the present. Okay, this is the definition of Markovian. This is not exactly the standard, but it is equivalent to the standard definition, because if also the present algebra is expected, the definition that I gave on Markovianity is equivalent to the standard definition of Markovianity, namely that the expectation on the conditional expectation on the past of a future observable is equal to the conditional expectation on the present of a future observable. Okay, this is the usual formulation of the Markov property. The first implication of the Markov property, as you know very well, is that since this S, this should be S as another misprint. This should be conditional expectation over S of the future of T is contained in AS, or if you want, the conditional expectation on the past of T of any observable localized on the future of T is contained in the present algebra of T. So if we restrict the conditional expectation of S, remember S is less than T, to the algebra at fixed time, we have a two-parameter family of maps from AT to AS, okay? And they are identity preserving. And then they have a strong positivity condition, which is called completely positive. I will not give the definition of complete positivity. It's a stronger form of positivity in the non-commutative case, but in the commutative case is equivalent to positivity, and that is why this notion of complete positivity did not arise in classical probability. So combining Markov property and projectivity with a simple calculation, you prove that the two-parameter family PST is in fact a backward evolution. That is, it satisfies the evolution equation that if I first go from T back to S and then from S back to R is the same as going from T back to R. Okay, so in this sense it's called the backward evolution. And similarly, you define forward evolution, of course. Now we will also use forward. Okay, so this is why we define a backward evolution just as we said before. it is a completely positive family of completely positive map, which is an evolution and is identity preserving, in the sense that the image of the identity of the algebra AT is the identity of the algebra AS. Okay. In the physical literature, these are called quantum dynamical evolution, but this is a pleonasm, because evolutions, by definition, an evolution is dynamical, so it's useless. So summing up, we have proved that every expected Markov process is canonically associated with a Markov backward evolution. In classical probability, we know that if the algebra, in classical probability, we correspond to the case that algebra A is commutative, the converse of this statement is also true in the following sense. There is the following theorem that you know very well, but it is only an algebraic formulation of a very well-known theorem in Markov processes. That is, if the algebra is commutative and the algebra for every finite set, the local algebra, roughly speaking, this is the algebra generated by the algebra AT with T belongs to F. And this is the algebraic formulation of the Kolmogorov tensor, of the Kolmogorov product representation for the sample space of a stochastic process. Okay, then we, given a Markov backward evolution, remember that is a two-parameter family from AT to AS, and S is less or equal typically than T. It is the identity when S equal to T under some continuity condition. Then, given the restriction, we call P0 the restriction of the state P, which is the analog of the probability measure P on the initial algebra. So is the initial distribution, P0 is the initial distribution of the process. And then we have the algebraic formulation of the famous formula for joint expectation of Markov random of products of Markov of random Markovian random variables at different times. We can suppose, because everything is commutative, that the times are increasing, and it's written here, and that the AT are localized at time t. And you see, this is the algebraic formulation of the classical formula for the joint expectations of a Markov process. Okay. However, there is a very big difference, because you see, up to now, the translation has proceeded very smoothly. We simply reformulated algebraically classical probability, and we proved in the more general algebraic framework some known theorems of classical probability. So without big surprises. However, here, for Markov processes are the first example in the transition quantum, classical to quantum, in which the smoothness of this translation breaks down. So as you can imagine, these are the most interesting situations, where for some reason, this easy algebraic translation breaks down. So why, I will try to just give you an idea why it breaks down. You see, look at the formula that we have seen before for joint expectation of Markov processes. So what you do, you first you do a backward iteration. You first apply the Markov operator to ATN, then you bring it back to time Tn minus 1, and then you multiply by the observable at time T minus 1, Tn minus 1. And then you apply again Markov operator, and so on until you arrive to the time 0. But the crucial point is that the map that to a pair, look at what we do at the last step. I took here the last step. We first apply Markov and then multiply. So this means that we have a pair, ATJ minus 1 and the image of ATJ by Markov operator, and you associate the product. You see, but you see, it's very easy to see that if you are in a non-commutative algebra, this product, even if A is positive and ATJ minus 1 is positive and ATJ is positive, this product may be even not self-adjoint. So it makes no sense to speak of positivity. So you understand why, if we try a naive generalization of this formula, we don't get a state, so we lose the probabilistic interpretation. We get a linear function, but not a state, okay? And so this is what I already said. So what is important of this formula is that this formula allows to associate an expected Markov process to a Markov evolution, but there is no reconstruction theorem. So if we start from the process, we can deduce a formula like this, but we cannot use a formula like this to reconstruct the process, okay? So we formulate, how much time is left, please? Can I know? Hello?
It's about 20 minutes.
20 minutes. So it is a standard fact that an evolution with some homogeneity property gives a semigroup, okay? It is a standard property. You introduce the shift operator and you require the homomorphism to be covariant by the shift. You require the conditional expectation to be covariant by the shift. And then the Markov evolution becomes a Markov semigroup. So remember, a Markov semigroup is a completely positive identity preserving semigroup on a certain star algebra. Now let us formulate the reconstruction theorem in the quantum case. In the quantum case, we have an evolution and we want to reconstruct the Markov process. How can we do? We said this naive generalization doesn't work. In quantum probability, there are 3 different solutions to this problem, and each of them has advantages and disadvantages. I will begin with the first, which is the most abstract one. I will not describe it in detail because it is very abstract and is essentially a generalized Steinspring or Kolmogorov Steinspring construction. It has the advantage that it is canonical. That is, it depends only on the initial distribution and the semigroup. And this is exactly what we do in the classical case. But it has disadvantages. That is very difficult to identify concretely the space and the algebra. So the processes that we obtain are not easily manageable. Then the resulting process is not a real Markov process, but a weak Markov process in the sense that the homomorphisms are not identity preserving. So in the sense that they depend on the image of the identity is a projection which depends on T, however. And moreover, when we have reconstructed the process, we have not this nice distinction between diffusions and process with jumps that we had in the case of expected processes, okay? The second solution is called the random walk scheme. Why random walk? Well, what is a classical random walk? You start with an initial observable, an initial random variable, and you add to it a random variable which is the increment of an independent increment process. So the random walk scheme is a generalization of this idea to the quantum case. The initial algebra can be arbitrary star algebra, but the algebra must be the analog of an independent increment process, and this is called factorizability. This is a natural generalization of the, let me describe it. What is factorizability? I restrict to tensor factorizability. There exists other form, for example, Fermi factorizability also is available, but I restrict to tensor factorizability, which is the one that we have in classical probability, okay? So you have a common intuition for this factorizability. And what is factorizability? If I have a partition of R in disjoint non-empty intervals, then the algebra BR is decomposed, isomorphic to the tensor product of the corresponding algebra localized on the intervals of the partition. So you recognize the property of the algebraic property of independent increment process. Then there is the statistical property of. Before the statistical property, let me introduce in the random walk scheme. What is the pass filtration? Pay attention. In the random walk scheme, there is the initial algebra. So we take the initial algebra included in the past filtration, but not included in the future filtration. This will be important for the construction. Okay, so there is an asymmetry between past and future in the random walk scheme. And now we come to the statistical property of infinite divisibility, which is the factorizability of the state. You see, just as the algebra factorizes into the tensor product of the algebra associated to the single intervals, also the state, which is the probability measure, will factorize according to the same partition. So this is the notion of factorizable set. So now the conditional expectation now in this framework are extremely easy, because they simply, as in usual independent and random walk, they simply cut out the future part by taking expectation in the future part. Okay, and what remains is the past part of the observable. Now we introduce the algebra fixed times. Remember, and to do this, we use a unitary Markov, a unitary multiplicative functional. Unitary means that each operator U is a unitary operator. Okay, so it's a particular case of multiplicative operator. Notice that now we are taking a right multiplicative, because the future is on the right of the past. So, and we using the right multiplicative functional, we can define, since by unitarity of U, these are homomorphisms of the algebra at time 0, identified with the time 0 multiplied the identity of the noise. This is an homomorphism for each t. So according to our star homomorphism, and so JT is an algebraic random variable, and we use this JT as algebra at JT of x will be JT of x0 will be the random variable at time t. Okay, now recall the form of the evolution associated to the Markov process. And since we have these independent increment properties, we have the following chain of equalities, which is extremely important and will be used used very much in the classical theory of random walks. That is, if you take conditional expectation on the past, but you see, UST is localized on the interval ST. So to take the conditional expectation on the whole past is the same as taking conditional expectation on 0, or even the same to take the conditional expectation in the complement of the interval where this is localized. Okay. So now, by construction, you see, because unitary isomorphism, this is more than homomorphism. It is in fact an isomorphism on the image. So we are in the homogeneous situation that the algebras AT are all isomorphic to the same algebra B0, the state algebra at time 0. Now we need this condition, which is automatically satisfied when U is a unitary operator, okay? And under this condition, we have, this is a theorem, but I will not prove it. We have contemporaneously, the two-parameter family PST is both forward and backward Markov evolution. This is very special of the independent increment process. I don't give you the proof of this statement because it is more technical. And so now, recalling this definition, S0 is localized in 0. U0t is localized in 0t. Therefore, xt is adapted process. Xt is an adapted process. So with the same notation, remember that ut, with the same notation as before, satisfies the stochastic differential equation. So we can look for the stochastic differential equations satisfied by the process x at time t. And with some calculation, you find that the process x at time t, remember, you deduce the stochastic equation of x from the stochastic equation of u. And for this, you need a quantum version of the Ito table, which exists in the framework, very general, that we are discussing. Okay, so now you have that xt satisfies the following the stochastic differential equation, in which you recognize, as usual, initial data, the drift term, and the drift term, which is this plus this, and the martingale term. So the drift term is all of this. But there are two martingale terms: the contribution of the point process, and the contribution of the diffusion process. Okay. So we have this stochastic equation for the process is called a forward quantum Langevin equation. But if the process is commutative, we have the usual Langevin equation. Usual, apart from the fact that the Hamiltonian term is absent, usually in classical probability. But if you work with the structure of multiplicative function, this Hamiltonian term is necessary. Okay, so now, since we have the stochastic equation satisfied by xt, we do as usual in Markov, the theory of Markov process. We take conditional expectation at time s. So the martingale term disappears because we take conditional expectation time s, and the interval of the equation starts at s. So martingale term disappears and remains only the expected version of the drift term. But since this belongs to the initial space and sigma belongs to the initial space, they come out of the conditional expectation. And here you see you reproduce the equation, because if you remember the equation of the evolution, it is exactly this. This is PST applied to XT. So we have this equation. Now let me show, this is this part of the drift term is very important, because you see it is a map which consists in taking the process xt and multiply on the left by m and on the right by m star. But this is a completely positive map. So even if we don't know precisely the form of this term, we know that this is a completely positive map. So the stochastic equation for the evolution equation can be written as initial state plus integral of the drift term, which is, there is a dt missing, this should be a little bit, the integration variable should not be t, but say tau, and there is a d tau missing here. And this, maybe we don't know what it is, but it is a completely positive map, okay? Maybe we don't know, because it is not a general structure. There is no general structure term. What this object is depends very, very much on the martingale term, on the structure of the martingale, okay? But the important is that it is completely positive. So why this is important? Let us explain this in the simplest case, when the Hamiltonian term does not depend on t, and the drift term doesn't depend on t, then, therefore, in this case, the evolution is a semigroup. And the semigroup as this, the evolution as satisfies this equation. Now, this is the differential form of this is the Fokker-Planck equation, which in the physics literature is also called a forward master equation. Okay, so you have this forward master equation, but now the semigroup is identity preserving. The semigroup is identity preserving. So suppose that B0 has a very special form, is the algebra of all operators, bounded operators on a complex Hilbert space, separable. Okay, then it is a known theorem that any completely positive map on this separable Hilbert space has this structure, in the sense that there exist operators belonging to B of H, such that the completely positive map has this form. And therefore, the Markovianity, infinitesimal Markovianity condition, because the semigroup preserves the identity. Therefore, the generator must kill the identity. And therefore, the fact that the generator, which was written here, the fact that this generator preserves the identity, since the commutator automatically is zero with the identity, it imposes the following constraint on the drift. The drift must be equal to the sum, in some sense, these operators Lj are a generalized square root of the drift. And the index J corresponds to the fact that the noise has many independent components. Okay, so we have the generator of this form. But this form of the generator, when the operators L, J are bounded, is the most general form of a quantum Markov generator, as proved in a theorem in 1976 by Lindblad in the general case, and Gorini, Kosakowski, Sudarshan in the finite dimensional case. So you see, we arrive deductively with the random walk scheme, we arrive deductively to the most general generator of a Markov process. But since this is the most general generator, we can, this will suggest to, well, I just mentioned that there is a huge literature devoted to the extension of this theorem of the structure of Markov generators to unbounded generator. The best result at the moment available is due to Fagnol and Chebotario, but I will not speak of unbounded case, okay? So, as I said, the fact that any Markov semigroup can be obtained, at least with bounded generator, can be obtained by a random walk type operator Markov process. So this suggests the following strategy to find solution of the Markov reconstruction theorem. Given the semigroup, remember the problem is this, given the semigroup, construct a Markov process whose canonically associated Markov semigroup is the given semigroup PT. And this in the literature is also called dilation problem. So the idea of the strategy is the following. You give the semigroup using the structure of the GKSL, Gorini, Kosakowski, Sudarshan, Lindblad generator. You try to find a stochastic differential equation which defines a unitary Markov cocycle, and then you define the process as we defined constructively in the deduction of the equation. Okay, so the idea is to use the stochastic generator of the generator of the Markov semigroup, and this strategy was successfully applied by Hudson and Partasarati in 1982, and these authors produced the first general method to find a solution of the general Markov reconstruction problem as an application of the boson they developed boson stochastic calculus, which is an example, the first quantum extension of Ito calculus, and has been the model for all subsequent extensions, which are many available. Okay. So the random walk structure gives the solution of the problem, but it has disadvantages. Why? Because the solution is not canonical. Why? Because it doesn't depend, as it happens in the classical case, on the semigroup itself, but on a particular expression of its generator. And there are many such expressions, and different expressions lead to different processes. So it's definitely not canonical. There are many stochastic processes constructed with this technique that are associated to a Markov semigroup. Second, it's not covariant because time zero algebra plays a very special role. However, there are many good advantages. The first advantage is that the method is quite general. And in addition to the boson generalization, there's a lot of other generalization, Fermi, free, monotone, finite temperature, a lot of different independent increment processes, which give possibility to solve the reconstruction theorem for Markov semigroup. Moreover, it allows to distinguish the jump part from the diffusion part of the stochastic equation. And it comes out canonically from physics. Albert mentioned our book with Wolovic and Lou on stochastic limit, and this book is devoted exactly to this, to show how, starting from usual Hamiltonian system of quantum physics, you get precisely this kind of quantum stochastic differential equations. Okay.
Excuse me, please. The time is finished.
Okay, so I will not speak of
1 or 2 minutes.
I want just to say the third approach in 1 or 2 minutes, just to say that this approach is based on an analysis of quantum conditioning, okay? And this analysis leads to a different class of Markov processes. I just want to show you the formula that you have. I just jump to the end and show you what kind of because this Markov, I will try to say why these Markov processes are interesting. Okay, I just give you the formula. So there are two formulas depending on the direction of time. One is the backward Markov process. You see, the joint expectation is obtained very similarly to the classical case. You bring back iteratively from time n plus 1 to time n, then you apply the generalization of the Markov operator, and you couple, but now the couple is tensor coupling, not multiplication. And this preserves positivity. So you iterate the process and you prove that this is positive. Okay, I think that this is enough because, as you have seen, the time is not enough to describe, but what I want to say only is this. When you restrict the quantum Markov process and you take all the initial algebra to be commutative, you discover a very nice new class of classical Markov process. And this new class has been proved since the early time of the theory, includes the so-called hidden Markov process. So essentially, a quantum Markov process is a huge infinite collection of classical Markov or hidden Markov processes. Thank you very much for your attention.
Thank you very much for your talk. And now questions, please, Елена Boguslavskaya. Елena, do you have question?
Yeah. Hello. Well, thank you very much for the wonderful.
Your comments, question.
Yeah. Thank you very much for the wonderful talk. I just in the beginning of your talk you mentioned that you should have some all the moments exist. I wonder if you relax this because I this condition at some point? And if you do that, where exactly do you do that?
No, the point is the standard construction. I introduced I emphasized the existence of moment in order to distinguish between operator algebraic processes and true algebraic process. And operator algebraic process must have all moments, but the stochastic differential calculus works for arbitrary algebraic process. I just spoke of operator process because to give you the a more intuitive formulation, which is more similar to classical probability. But all this discussion does not require the existence of finite moments of all orders.
Thank you very much.
Dear colleagues, please, in other comments or questions, please. Dear Professor Accardi, thank you once more for your seminal talk. We hope to see you next week at the same time.
Yes.
And now I will give a short announce for the next talk. In English, deduction of quantum theory and its extension from classical probability. На русском это вывод, насколько я понимаю, вывод квантовой теории, ее расширений из классической вероятности, из классической теории вероятности. Ждем всех на следующем докладе. Wait for everybody on the next talk of Professor Accardi. And now, thanks once more.
Thank you very much for attention. Thank you.